Now we want to show that this rate region R is also optimal. We already have shown that we can achieve that. So let's start. Again, we start in the same way. So we start with R1. So we know that there are 2 to the n R1 indices W1. And W1 is a function of xn. So like we did every time we start with this inequality that n times R1 is greater or equal than the entropy of W1. Now, of course, we can make it smaller just by adding here a condition at the entropy, because the conditional entropy is smaller than the entropy. So this is smaller than the entropy of W1 conditional on Yn. Now look at this entropy here. So the entropy of W1 conditionally on Xn and Yn is 0, because W1 is a function of Xn. Therefore, this is 0, and we just can add it. But if we add this here, we can write this as a mutual information. The mutual information between Xn and W1 under the condition Yn. And this mutual information we can write in another way. We can write it as the entropy of Xn conditional on Yn minus the entropy of Xn conditionally or condition on Yn and W1. Of course, we know that all X are identical distributed. All Y are also identical distributed. So the entropy of Xn under the condition Yn is equal to n times the entropy of X and Y. That's the first thing which we want to apply now. So we replace this term here by this term here. So then we know in totally starting from here that n times R1 is greater or equal n times the entropy of X conditional on Y minus the entropy of Xn conditional on Yn and W1. Now we add here this condition. Why we can do this? Because W2 is a function of Yn. So we can add this condition, and the entropy here, this is the same like this. And now x hat of n is a function of W1, and y hat of n is a function of W2. For this reason, still by adding this condition here, this entropy is still the same. So we can write this in this way here. Now we remove some conditions. So we remove the condition Yn, W, and W2. When we do this, this entropy can only get bigger. So the total term can only get smaller. So we know this term here is smaller than this term here. But now here we can do what we do every time, or most of the time. We apply here our Fano inequality and can write here minus n times PE log 2 of x, the cardinality of x times the cardinality of y, plus binary entropy of PE over n. Now we know that this term here goes to 0 if n goes to infinity, and so we have proved that n times R1 is greater or equal n times the entropy of x conditional on y. And the n cancelled out, and we have the first part of the rate region proved. Of course, for R2, we can do it in exactly the same way, but then we have h of W2, and we have here W2 under Xn, and so on, and you just have to replace W1 by W2, Yn by Xn, and Xn by Yn. Then you can do the very same steps and get that n times R2 is greater or equal n times the entropy of y conditional on x, and you get R2 is greater or equal than the entropy of y conditional on x. Then the next part, normally you should know why this is true, because already if we use two encoders which work together, we know already from the theorem we have in the first section of our script that R1 plus R2 is greater equal the entropy of the joint distribution X and Y, because if these encoder work together, that's the best what they can do. But we can also do it differently. We can use the same tricks here and the same steps, but if you compare this with the calculation we did for source coding with only one emitted sequence, that's really the same proof. So this is nothing new in principle. But we know here now that this bound is also best possible, and so in totally what we get is that this is a best possible rate region. We cannot beat this rate region.